Alright, sorry for the shaky cam, but I just want to get this over with. Alright, so this is workshop 11. I've also have an addendum to make to an earlier bit that I did where I made a mistake. So if you learned how to do something wrong, I apologize. I'm going to start with workshop 11 though. Okay, so let's see. Find the Fourier series for the following functions on the given intervals, and I can use these formulas to get the integrals for free. The function f defined by f of x, so it's 0 from -2 to 0. It's x from 0 to 1, and it's 1 from 1 to 2. So there's a graph of our function. This is the Fourier series. That should be like capital F, or the Fourier series of a function is going to be a0 over 2 plus this summation, and you gotta find a0 and an and bn, and this is how you get a0, and that's how you get an, and that's how you get bn. So back to the problem. So let's just start by finding a0. So the function, it's not like, if you look at the graph, it's not like necessarily even or odd. It doesn't really follow those. So you pretty much got to evaluate find all three of these. They're all going to exist. So a0 is 1 over L, the integral from minus L to L of f of x. So f of x is different depending on what interval you're in, right? So here it's just going to be x, and then here it's just going to be 1. So I can just split the integral up and evaluate from 0 to 1 for this one, and then from 1 to 2 for this guy. And don't forget the 1 over L. So it's 1/2, and then I integrate that, and I integrate this, and evaluate that integral, and I get a0 equals 3 over 4. Now, a0 over 2 is something you got to remember as well. Don't forget to divide by 2 when you put the whole thing together. So anyway, we got a0, that's cool. An, 1 over L, the function times cosine of n pi x over L dx. So again, our function's different, so we have to split this integral up depending on what interval we're talking about. So from 0 to 1, it's going to be x, and then from 1 to 2, it's 1, right? So let's integrate this. We get those formulas for free from up top. So this is how you evaluate that integral. So it's x sine ax over a plus cosine ax over a squared. So this is a n pi over 2, right? So it's x sine of ax over a plus cosine of ax over a squared. So that's this one. And then this one here is just the regular integral. So you get sine there, and then, right? Yeah. Sine is cosine. All right, cool. So, all right, so just evaluate this now. So from at 1, it's just going to be sine n pi over 2 over this, plus cosine n pi over 2 over that. And then 0, sine of 0, well, that x becomes a 0, so that disappears. And then it's cosine of 0, right? So that's always going to be 1. And then this one, we're going, I didn't show me doing it from 1 to 2, but that's what I'm doing. So 1, or so, sorry, yeah, from 1 to 2. So at 2, this one is just going to be sine n pi over this, and then minus sine n pi over 2 because it was 1 here. So then we just combine all of those together to get this. So it's 1/2. So you can see that this guy and this guy are going to cancel. I'll just keep the 1/2 outside here. So we'll just be left with this and that. And then they're over the same denominator. I just took this 2 squared and put it up top, and then factored it out and got this. Now in his answers, he did this wrong. So he didn't multiply by his 1/2. See, everything's the same here, right? But then he didn't multiply by 1/2 afterwards, so he got a different answer. I think that's he made a mistake there, so whatever. Anyway, so bn, it's the same kind of thing, except the function gets multiplied by sine. So you do the same thing. It's different function along that way, so you got to make sure you get that straight. So it's just minus x cosine x plus sine, right? Alpha x, whatever. Anyway, you can just look at those integrals up top again. So yeah, let's evaluate that. So at 1, yeah, at 1, we get x was 1, right? So we get this, and then sine was this, and then at 0 it's 0 here, right? So that becomes 0, and then sine of 0 is 0 also. And then this one, we go from 2 to 1, so cosine of minus cosine of n pi minus cosine of n pi over 2. Combine all that together. These guys will cancel, and you'll be left with this. I took the 2 squared and put it up top. I took this 2 and put it up top. Alright, so then what did I do here? Let's see. Oh, I distributed the 1/2 to each of them. And then the other thing is this one here is going to alternate between 1 and -1, but you just need to pay attention to when it is. So like at n equals 1, this is just cosine of pi, which is -1. -1 times -2 is going to be 2, right? Oh, wait, sorry. Look, with this 1/2, so it's just going to be, this 2 is going to be just a 1, right? So it's going to be, sorry, it's minus cosine of n pi, right? So at cosine of n pi at n equals 1 is going to be -1 times -1, so that's going to be +1. So I'm putting in -1 here, so when n equals 1, it's going to be this squared, right? So you can rewrite it like this. I don't know if he explicitly wants it like that. Yeah, I mean, I'm sure you could just leave it like this and it's fine, but I mean, he's been doing it, so I just wanted to make sure I knew how to do it. So now what you can do is just take bn. All I did here was just, I wanted them over the same denominator, so I could just factor that out and have this. So that's bn. So the Fourier series is going to be a0 over 2. So a0 was, oh God, 3 over 4. Sorry for the shaky cam. Okay, so 3 over 4, that becomes 3 over 8 when you divide it by 2, plus, and then, so this is an times cosine of n pi x over L. And so that was an, this thing, and then bn was this whole thing times sine. So that's the entire thing. I just went ahead and factored the pi over 2 out, because that's what he did. And then put it on the bottom over here. So that's how you do the first question. So here's the second question. So the function f of x equals minus x on the interval of minus pi to pi, and then just take advantage of this stuff. So f of x equals minus x, it's basically it's got some symmetry there, right? Because it's not like piecewise or anything like we had in this one, right? I just kept this here just so I could do the integrals quickly. But yeah, so f of x is an odd function, right? Because it's symmetric about the origin, and so therefore all your an terms are going to be 0, because if it's an odd function, and remember that the an gets multiplied by cosine, which is an even function. So, sorry, for an, you're taking your function, you're multiplying it by cosine. So it would be an odd function times an even function, which will give you an odd function. When you evaluate an odd function from minus L to L, it's going to be 0. So that's why we can just do away with all the an terms right off the bat. So this one here, bn is 1 over L minus L to L, f of x sine. So this here, because it's an odd times an odd, it becomes an even function. That's why it has a value. And then for even function, they're symmetric about the y-axis. So you can just evaluate from 0 to your interval and just take 2 of them. It's just double, right? Like think about the integral of x squared. You go from -1 to 1. Well, it's just like going from 0 to 1 and multiplying that result by 2, because it's the same positive area. Anyway, back to it. So that's why I got a 2 up here now. So it's just this. So we can use this one here. So I should get minus x cosine of nx over n, right? And then sine of nx over n squared. And so we're going to evaluate that from 0 to pi. So for pi, it's going to be this and this. And then for 0, that's 0, and then sine of 0 is 0. So then we get this. I also wanted to make sure that I kept this here, but I wanted to also show in another step. I didn't want to do too many steps at once. N pi, well, like the sine of pi is always 0. The sine of 2 pi is always 0. The sine of 3 pi is always 0. So it's just going to be 0 here. And then I've got this, and then it's a negative negative, so then I just got those to cancel. So now I got this, and then we can rewrite this because this will just alternate from -1 to 1. So at n equals 1, this is -1 pi, right? So that's why we can just have n. We don't need n plus 1. If we had a negative here, we just use n plus 1. But anyway, so that's what bn becomes because these pi's will cancel, and we get this. So the Fourier series for this one is just going to be 2, because I can take that out. And then that's bn times sine of n pi x over L, but L in this case was pi. So that those pi's will cancel. So that's the Fourier series for that one. All right, the Fourier sine series of the function f of x equals 2 minus x on the interval from 0 to 2. So the function here is only defined from 0 to 2, right? So the green is the function. And then for a sine series, basically this becomes an odd function over here. So you just have to like basically flip it about the origin down here. So because it's an odd function now, we're treating it as if it's an odd function. ANs are going to be 0. So it's 1 over L times the integral from minus L to L. But because this was an odd function times another odd function, it's an even function. So you can put a 2 up here and evaluate it from 0 to 2, which is good because that's what you need to do because you need f of x, right? But it's not defined down here. So we can just treat it like this. So now, just compute this integral. I just decided to split them up. So then I get this one here for the first guy, and this one here for the second guy. And then, so this becomes 2, what was this? Oh, that 2 came up here. And then this 2 and 0, so this becomes n pi. And then for cosine of 0, it's always 1. So we get this. And then that minus minus canceled, so that's why that's positive 4. And then 2. Okay, so 2 times 2 is 4. Cosine of n pi over n pi. And then this one here is n pi over 2 squared. But this was at 2, so that's also 0. I showed that in a separate step up in the last one, but basically it's, you know, a multiple of pi, so sine's always going to be 0 here, and then 0 and 0, that becomes sine of 0, which is always 0. So that when you consolidate all these, you get these guys will cancel, so you're just left with this. So that's your bn. So this is the sine series. You just take that bn times sine of n pi x over L, and L went from, L was 2, right? Okay, cool. So I now do the exact same thing, but now do a cosine series, which means just turn it into an even function, right? So now all the bn terms are going to be 0. So now we have to get a0 and an. So a0 is going to be an even function now, right? Because this was this is now an even function times an even function. Well, sorry, this is just an even function. So we can multiply by 2 and evaluate from 0 to 2, which is what we're supposed to do because that function's only defined from there to there. So then we get this, and then we just plug this in and compute it. So we got a0 equals 2. And then an, it's the same deal. An even function times an even function is an even function. So you can go from 0 to 2 and multiply this guy by 2. And then we'll just compute this integral. I just split it up again, and then did this one separately, did that one separately. So this becomes 2 sine n pi. Sine n pi. That one should also be 0, shouldn't it? Okay, well these are 0 anyway, and they cancel, so it doesn't matter. Maybe it's just best to write it all out, and then you're less likely to make a mistake and make an assumption. Okay, and then this one I also computed that way, so this was 2 n pi, and then this is n pi, so that one's going to alternate, minus 0, and then cosine of 0 is 1, so we got that. So when you combine them all together, you'll notice that, oh sorry, you'll notice that these guys will cancel, and then we're left with this. Remember that negative, you got to distribute that, that negative, and that negative, make that positive. So then we've got, remember I said this was going to alternate, and that 4 came from down here, but it has to start, so cosine of pi is -1. So it's -1 times a negative. So it has to be positive when n equals 1. So when n equals 1, this term gets squared and we're all good. And then this one, the 4 just came from down here. So then that's an. So then the answer is going to be a0 over L, a0 over 2, and a0 was 2, so 2 over 2 is 1, and then we get this times this shit. Oh yeah, he had it written like this. You could leave it like this, it's fine. But just think about when n equals 1, that term has to get squared, and then you add 1 to it. So it's like the same thing as, you can put a minus in front of it as well. That would work also. So anyway, it doesn't matter. But just keep going. So this, oh yeah, this one. Oh god. All right, I'm gonna try to explain this. I might butcher it. I'm not sure. I actually have to. I'd like to go over this with him in his office hours if possible. But here we go. Okay, so f of t equals minus t, and we want to find the general solution for it on this interval, right? So we have to use Fourier series to do it. So it's periodic. The period's 2 pi. So I just drew it from, this is the interval we're concerned with, but really what happens is when you go 2 pi from here, it's the same value. That's what it means to be periodic. So, and also it's odd, right? It's odd because, well, it's not symmetric about the y-axis. That's basically it. So all your an terms are 0, so at least there's that. God, if he gives us one where, anyway, whatever. If he gives us one that isn't symmetric about the origin or symmetric about the y-axis, I don't know what I'm going to do. But anyway, let's go ahead and do this. So I had to compute this again, but actually it's the same integral that we did in the last one. So we can just fast forward until we get to here. So this is Bn, so this is the Fourier series of it. Okay, so the particular solution, actually I need to change my notation real quick because I did change it before. So this is B. I'm going to make this a capital B just to keep things consistent. All right, so the particular solution is just a generic one. This capital Bn is not this Bn, okay? So this is a generic Bn. So for yp, let's go ahead and take the derivative of that. So it's just n times this. Oh, sorry. This is that. This should be cosine. Sine derivative. That will be cosine. And then times what's in here, right? That would give you n, and then you get this one here, and this one's supposed to be negative. I found this out towards the end, and I didn't notice his negative sign when it was falling through. So these are like your yp's, quote unquote. So just for the homogeneous, we have an auxiliary equation. Oh yeah, I don't know if I highlighted what that actual differential equation was. Is y double prime plus y equals f of t, and this was f of t. So for the homogeneous, let's just find our solution for that. So we use an auxiliary equation. We get complex roots, so our solution looks like this. So yp plus yp double prime has to look like this, right? So here's my capital B's, right? So this was yp, and this is yp double prime. So we need to have it where our roots are going to match. Our roots seem to match when n equals 1, because then we have sine t, and we have sine t here. So at n equals 1 is what we're going to use. So what we're doing is we're just going to take the first term out of these guys. So y1 is just going to be, in general, it's going to be this, right? Because our roots matched. And I'm multiplying by t because our roots matched. And then I'm going to take the derivative of that and get that, and then take the second derivative and get this. And then I'm going to add them together, and that has to equal the Fourier series evaluated at n equals 1. only, right? So at n equals 1, our original Fourier series had this, right? 2 times minus 1 to the n times sine nt. So at 1, this is going to be sine t. This is going to be negative 2 over 1, right? So negative 2 sine t. That's where this comes from, right? Oh, I could have just shown that. So anyway, this is y1. I need to change that. Hold on. Y1. There. I don't know why I had a prime term there. Anyway, I didn't use it as such, but anyway, so that's y1 was this. It's like yp at 1, if you want to think of it like that. This is yp double prime at 1. So then we get all this to cancel. So we've got this, and that has to look like this. So b's got to be 0, and a has to be 1, because we got the minus 2 there. So our particular solution is going to be, remember I said yp was this, sorry. Oh, it was back up here. Yeah, yp was this, right? It's basically this plus that, right? Right here, this guy. So I said that yp is going to be the first one. Remember we took the first term and we were like comparing all this? Well, we still have all the other stuff left over. So it's going to be these, but now they're evaluated at n equals 2. So, and then this capital BN, basically what it has to be is, if it's going to match up with our regular solution, like this BN has to equal this. Because look, if you factor this BN out, it's 1 minus n squared BN. So that was our original BN. So this BN is going to be our original BN, which was 2 minus 1 to the n over n divided by this. And then, yeah, so the series starts at n equals 2, so we don't have like a weird discontinuity, because if it was 1, that would be divided by 0 and all that shit. So yp equals t cosine t, because it was a t cosine t, and a was 1, plus bn sine nx. So this bn, this is not, sorry, this notation's wrong, so I need to fix this. This is why I was worried about doing this video. It's going to be this, right? So in general, or sorry, our particular solution looks like this, and this is our capital BN. So he did this stuff beforehand, so I probably should have done it like that. So this line, I think, is you could consider it wrong, because you could write this as little b, and then that would work, I guess. If you want to make it, yeah, because then, no, it wouldn't be little b. Anyway, sorry, I digress. I'll recap it in a minute. And then, so this yp, you just add to the yc, and then you get this. So again, just to tackle this quickly, you find out if your function's odd or even, and then evaluate these if you haven't done it already. We did it in another question. So then you get your Fourier series. So this is your little b, and then your particular solution is going to be some generic b sub n times this, and then you take the derivative of that and derivative of that, and then you solve your homogeneous. And then basically what you're looking at is you want your yp plus yp double prime to match your yc solution. So you're basically looking at values of n that are going to make that work. So if like n was 2, and like this and this was 2t and this was 2t or something like that, then that's the one that would match. So then you'd have to evaluate at n equals 2. So then that would mean you'd have 2 terms. So I hope he doesn't do that. But anyway, so then what you're saying is you're going to find roots that would match, make them match. And then you should then calculate your capital BN. So your capital BN is basically going to be whatever these work out to be when you do the derivatives. So this plus this is your particular, is like your differential equation, right? And it has to be equal to the Fourier series. So if you have, and your Fourier series over on the right hand side was this one, right? So you know that um, this guy plus this guy has to be uh, this guy. This little bn, so everything's the same. So this little bn is equal to um, this big bn. That's 1 minus n squared times the big bn, if that makes sense, because these already match. So your big bn is going to be that, right? And then that is what's going to go once you, like, so because we had a matching term at 1, this one's the rest of your particular solution, right? That's where this came into. And then you have to do all the other shit. So you, once you found the value that it worked out at, then you once you found an n value that it worked out, evaluate this guy at that n value, and then you'll come up with these, right? These matched, so that's why they're getting multiplied by t. So I think they have to match. That's the only, that's what I wanted to ask him. Like, do I have to find ones that match, or do I just have to find any ones in the interval that I can evaluate? Because basically I have from 0 to 1 to 2, right? To pi, oh, I have up all the way up to pi, so I could even have 3, but like, why not just use 1? Does 1 work? Because like, you can use the 0.1 because it's not at these weird like sections where it's iffy to plug that number in. But sometimes, like, you know, like if you do the Fourier series, you'd have like maybe a point here, and it's the average between these two. Then I think you might be able to use that point to plug in. So this is why, like, it's important to kind of like, for me to talk to him to get my head around this a little better, because like working reverse engineering how this all works based on one example is kind of like iffy. And I mean, I've only got the worksheets to go on. If I could do the worksheets, then chances are that's going to be similar to the stuff on the final, because that's usually how he rolls. But anyway, so I hope that helped. Lastly, I just need to find the section that I messed up in. So I'm not going to look through the camera because it'll take me too long to find that. It was in the Heaviside functions somewhere. Oh, no, not that one, but it's on the same worksheet. Okay, here we go. These two. So what I did before, remember I was like, okay, I've got this function is t. Oops. This function's t at from 0 to 2, and then it's 1 minus 3t at t greater than 2. So basically I've got like t for the first bit, and then it turns on at t minus 2. And what do I have to do to this to make it this? Well, I have to subtract 4 t's and add 1, so I get that. And then I was like, okay, and then you evaluate your t's here at t minus 2, but it's t plus 2. And I made a mistake because I had t minus 2 here, so it would be minus 4 times t, and then minus 4 times minus 2, and then I wrote minus 8, so I made a mistake. So I just happened to get the rest of this right because of that, but it's actually, if you plug in t plus 2, this will work. Same thing for this one. Well, this one I had an extra term because I did it improperly. So you got t here from 0 to 1, and then t minus 2 from 1 to 2. So what do I have to do to this? I need to subtract 2 from this, and then what do I got to do to this to make it 0? I got to subtract t and add 2. So at the start it's t, then at t minus 1 you subtract 2 from it, and then this one at t minus 2 you have to subtract a t and add 2 to it, and then this t gets evaluated not at t minus 2 like I said before, but at t plus 2. Okay? So if you can keep that straight, then you should be able to get that right. So then I get minus t minus 2, and then these 2's cancel. Now before I had minus t minus 2, so this minus 2 became a plus 2, and then I had a 4, so I had an extra term here, right? Because it was a It's going to be 4 minus t, right? So I had a whole other term here. So anyway, you do inverse Laplace of that. You get 1 over s squared. This one, it's minus 2 over s times e to the minus s. And then this one is basically it's minus t times u of t minus 2. So minus t would be 1 over s squared times e to the minus 2s. So that's it. Good times. So have fun on the exam.